Hello, statistics scholars. This is Dr. McNeil here. Welcome to week 3. Our course has gotten off to a great start. This is a very short term semester. The semester term is much briefer, so we have to move quicker and more efficiently. And usually I wouldn't start the video lecture component of our class until week 7. But we don't really have that luxury. As I just said, we have a much shorter time to cover a lot more material. Chapter 3 is a good place for me to step in and give some instruction because we're talking about, in this chapter, two very important concepts in statistics. And those concepts are measures of central tendency and measures of spread. Measures of central tendency are probably the measures that people have the least difficulty in sort of wrapping their mind around. Whenever we're measuring something or observing a phenomenon, let's say we want to measure the height of fifth graders. Well, some fifth graders are tall and some fifth graders are short, but most fifth graders' heights will sort of move to a middle number, let's say 5 feet 1 inch, right? So measures of central tendency attempt to describe the data set with a single number that represents the entire data set. And we have 3 measures of central tendency. They are mean, median, and mode. All 3 of those terms describe how data moves to the middle. Mean just simply is the arithmetic average. So you take the number of fifth graders, add up their heights, and divide it by the number of fifth graders that you have, and that's the mean or the average. The median is the exact middle. So if we had a group or a data set of 5 fifth graders, the third value would slice it in the middle. So there'd be 2 values or 2 heights above and 2 heights below. Or if we had 4, it would sort of cut in between position 2 and 3. But all median really does is split the data in the middle. So half of the data values are above the median and half of the data values are below the median. Mode is the value that appears most often. And so it's possible that a data set may not have a mode, meaning there is no single value that repeats, or a data set could have a single mode. We would call that unimodal, or a data set could have 2 modes, which we would call that bimodal. It's even possible for a data set to have more than 2, and we would call that data multimodal. By the way, it's a good moment to inform you, you're going to encounter this in the chapter if you haven't already read it. Data is actually plural. So when we say data, we're talking about more. We're talking about a lot of data, more than one. A single data is datum. So hopefully that makes sense. So I said we have 2 main ideas. Measures of central tendency, I just described those, mean, median, and mode. And the second measurement are the measures of spread. And there are 5 measures of spread. 3 of them are very, very easy and intuitive. There's the minimum and the maximum. So whatever the smallest value is the minimum, the largest value is the maximum. And then we have the range. Range is the value when you take the maximum and subtract the minimum. That's the range. Actually, we have 6 values of measures of spread. So minimum, maximum, range. Then we have sum of squares, variance, and standard deviation. Now, those measures are really where people get tripped up. So my purpose today is not only to introduce the video lecture component of our class, but also to introduce an element of the class where I'm going to work out. You're going to see me actually work through a problem on paper. Now, since I'm introducing this to you for the first time, let me tell you how to use this video lecture. You should use the video lecture at your leisure. Sometimes they could be up to 30 to 45 minutes. You don't have to listen to it all in one sitting. You can stop the lecture, rewind it, and you could revisit it many times until the concepts are pretty clear to you. My goal is to help you overcome, if you have any, I can't tell if you have any, but my research suggests that many students have a fear or phobia of statistics, and they relate that fear or phobia to generalized math anxiety. Sure, there is some math in statistics, but really statistics isn't math. Statistics really is the study of language. So, as I just said, there are measures of central tendency and measures of spread. That's language. You have to understand what that language means. You have to interact with that language. A lot of times, what I find is that students sort of are not attracted to mathematical terms, and so they resist them. And if you resist the terms, you're actually resisting the major part of learning. So I always suggest that as we move into each new chapter, that you pay attention to the terms. And in fact, I always recommend that students keep sort of a journal, a running journal of the terms that they encounter. And when you encounter a new term, and I'm going to walk you through that, to write the term in your own words so that you're beginning to make very important connections. So that's my setup. I'm going to go and introduce the the beginning of chapter 3. I'm going to introduce a couple of new terms. I'm going to leave really the bulk of the reading this week, as I have in the previous weeks, to you. But I'm going to demonstrate on the mat, what I call the mat, meaning we're going to work it out together, um, how to reduce data, how to take data from a data set and reduce it from its original data set all the way to the standard deviation. You may not even really understand what the standard deviation is right now. That's okay. I really just want you to practice the move. So I'm going to go through an example that's on page 64. My sense is, even though the example is fairly clear, and I really love this textbook. In fact, I'm in the process of writing a companion textbook, statistics textbook. I never thought I'd be doing that. For statistics instructors to help them bring the topic alive so that students have more connection and more interest in statistics. Because, quite frankly, I think statistics is fascinating. However, I'll share in later weeks. It really I took an undergrad statistics course many, many years ago, and it really, really derailed me. It undercut my confidence. And it was because the teacher didn't really help me make practical connections. And I'm very committed to having my students make those practical connections. So let's get started. Let's head over to the textbook. Um, let's take a look at chapter 3 and the concepts that describe measures of central tendency and measures of spread. That is the work that we're going to be doing quite frequently through the rest of the course. So it's really important that you understand these concepts now at this stage so that they don't give you much difficulty as we get to some more advanced stages, like chapter 7, which things get really interesting. Okay, so here we have our textbook, and it talks about, it gives us some key terms, and I think the textbook, as I said, is really conversational. It's easy to read. They give good examples. There are a few errors in calculations, but I'll make sure to point those out. And please, if you find any, you point them out for me as well. All right, so I'll introduce the terms arithmetic mean central. That's just another way of saying the average. Tendency degrees of, we'll talk about that a little bit. Freedom dispersion, interquartile range. I described to you already median. median, and mode. And I've been talking to you about the mean. I talked to you also about the range. But what I want to demonstrate to you is the impact of spread. And I'm going to do that by showing you how to calculate the sum of squares, introduce the term of variability and variance, and standard deviation. Again, that's where lots of students, myself included, really often have difficulty. So undermined, I felt, after statistics. It took me maybe 20 years to have the courage to go back to school to get my terminal degree. So hopefully your understanding and your ability to connect to these concepts don't derail you, which is my goal. Let's jump down to page 64 in the textbook and take a look at this data set. This is a data set. And I'm going to work through the data, but I recommend that you read the chapter and particularly pay particular attention to this section because it gives you the demonstration of how we calculate the variance for these quiz scores and how we take it all the way from this data set of X, how we move it into what's called absolute deviations. I'll explain that in a second, how we square those deviations. And then there are two methods that we can have to create the sum of squares and also move from data set all the way to standard deviation. So I'll show you those. I'm going to use the values. I'll explain that in a second, and then we're going to work it out on the paper. So here's X. X represents student scores on the quiz. And this is there are 20 scores. So the N size, N equals 20. And if we were looking at this as an N, that's a population, the N we would use would be a capital N. But if we're looking at this N as a sample, we'll use a lowercase n, but still, there are 20 scores. You can count them very easily. Here we have the formula for calculating the sum of X. We have sigma X, which means add up all the X values. When we add them all up, they equal 140. And then the thing that we have to do is figure out the average or the mean of X. The formula, which I'll show you for figuring out the mean, is the sum of X divided by N, capital N, or the sum of X divided by lowercase n, capital N if we're talking about a population, lowercase n if we're talking about a sample. Well, let's just stop for a second. This is most likely a population. We're really just looking at the population of these scores in this class. However, if we were taking a look at these scores as representative of other classes, we would use this as a sample. But I'm going to show you the two methods because there are two different calculations that we have to use if we're looking at it as a population or if we're looking at the data set as a sample. So here's what they don't show you. They don't show you that adding up the X values is 140, but to get the mean, it's 140 divided by N, which I told you was 20. And that gives us 140 divided by 20 is 7. So the mean of X is 7. I'll come back to this formula down here a little bit later. I'll talk about that. This second column is what we call absolute deviations. So now that we have the value of the mean, which is 7, we're going to subtract 7, which is X, from we're going to subtract 9, which is X, and we're going to subtract 7 from every value. So 9 minus 7 is 2, and here we have, again, 3 9, so that's 2. 8 minus 7 is 1. 7 minus 7 is 0. 6 minus 7 is -1. So that you can see these are absolute deviations from the mean. And when we're creating, this is called the sum of squares table. When we add up the absolute deviations, if our calculations are correct, it should equal 0 or very close to 0. Sometimes with rounding errors, you don't quite get a flat 0. But as long as it's very close to 0, you've done your absolute deviations correctly. This next column is called squared deviations. And the purpose of this, I'll explain this more and more throughout the semester, but this is the first time you're hearing it from me now. The purpose of squaring the absolute deviations is to get rid of the negative numbers. You can see how we have a negative number here, but now if we look at the column of squared deviations, there are no negative numbers. What we've done is taken 7 out of the data, because that's the mean, and we just have the absolute deviations from 7. And now we are squaring those absolute deviations, and squaring is just taking a number times itself. So 2 times 2 is 4, 1 times 1 is 1, 0 times 0 is 0, and when you use an exponent, if the number is negative, it turns it into a positive. A negative times a negative is a positive. So -1 times -1 is 1. -2 times -2 is 4. So when we add these all up, that equals, because they're squared, this is called the sum of squares. When we add that all up, that equals 30. And once we get the sum of squares, we're home free, meaning we can go from sum of squares to the variance to the standard deviation. And I'm going to show you those calculations. It's here in the book, but I think it's always better to sort of see and hear how the calculations work so that it's less confusing, less intimidating. There is another way to go from the data set of X to the standard deviation, and it doesn't involve the absolute deviations and the squared deviations. We skip over this, and you're going to see that in my calculations, and we go right to squaring each value of X. So 9 times 9 is 81. 8 times 8, or 8 squared, is 64. 7 squared is 49. 6 squared is 36. 5 squared is 25. When we add that all up, that is called, it's not called anything, but it's the sum of all the squared x's, right? So we squared all the x's, and then we sum all the squared x's, kind of like we summed x here. And there's a formula that we use to create the sum of squares without doing the absolute and squared deviations. Both are correct. It just depends on which you feel more comfortable with. I'm going to show you both. I'm actually going to test you on both, so you should know what the differences are. And it's also a good time to understand and begin to recognize and memorize the notations, because we have certain notations that if we're thinking about it as a population, and different notations if we're thinking about it as a sample. All right, if that's a little too confusing, no worries. Let's just jump onto the mat, and I'll work through the problems, and I'll also give you a sample problem that you can work on as an opportunity to earn some extra credit points this week. All right, so here I have a duplication of the data, right? And there are 20 values, exact counts of the data before. And so here are the steps. You're going to first calculate the sum of x and the mean of x. I'm going to show you that. Then we create the absolute deviations. I showed you that, where we're subtracting the mean from each value of x, and the mean happens to be 7. And then we're going to square the absolute deviations to get rid of the negative numbers and to calculate the sum of squares. And once we've done that, that's absolute deviations, squared deviations, then we're going to calculate the variance. The variance, if it's a population, here's the symbol for variance, it's called sigma, and a superscript 2, meaning that it's squared. We're going to divide the sum of squares by n, and n happens to be 20, right? Let me write that here. N equals 20. That's if we're talking about a population. N equals 20, and that's a lowercase n if we're talking about a sample. So remember that difference. Population, sample. So we are going to, as I said, we're going to square the absolute deviations, add them all up. That equals the sum of squares. And then if we are creating a population variance, we're going to divide the sum of squares by n. If it's a sample, we're going to divide the sum of squares, same number, by n minus 1. So n minus 1 would be 19. Right? And then we're going to create the standard deviation. And all we're doing for the standard deviation is the square root of the population variance and the square root of the sample variance. If that's a little bit confusing, don't worry, I'm going to show you how it works. So here, let's start with the first step. We have the sum of x. We're going to add them all up. I don't have to show you that. You can add this up for yourself. But the sum of x is 140. That's very easy to see. Now we need the mean of x. Now we have different symbols for whether it's the mean, it's a population, or if the mean is a sample. The symbol for mean for population is mu. It looks like a U, right? The formula is the sum of x divided by capital N. Or if we're talking about a sample, it's the letter M, capital M. And we're going to still use the sum of x, but this time we're going to divide it by lowercase n. All right? So the values that we would fill in here, the sum of x is 140. And n is 20. And here again, 140. N is 20. And the mean is 7. All right, so we have the mean if it's a population, mu, or m if it's a sample. So we're just going to subtract 7 from each of these values. I'm just going to put it on each unique number so you could see it. So 9 minus 7 is 2. Put that 2 there for all of those. 8 minus 7 is 1. Put the 1 there for all of the 8s. 7 minus 7, 0. 6 minus 7 is negative 1 because 6 is smaller than 7. Negative 1 for all of the 6s. And 5 minus 7 is negative 2. Okay, so we've done absolute sum and the mean of x. We've done the absolute deviations. If we did the absolute deviations correct, when we add them all up, they equal 0. So there's an easy way to do that here. We can just cancel them out. It's not that easy with a larger data set where the numbers are a little bit different, but it's easy to do it here. We're going to cross out every negative and positive number. Here's a positive 2, negative 2, positive 2, negative 2. Let's get rid of the 1s. 1, 2, 3, 4 ones. 1, 2, 3, 4 negative 1s. We have 1, 2 left, and 2 negative 1s left, and the rest of these are 0. So if we add them all up, you'll see that the sum of the absolute deviations is 0. So we know that we've done it correctly, and we can move on. If the sum of the absolute deviations is not 0, you have to go back and do it again. That is perhaps a reason to do the alternate way, because you don't have the extra step of the absolute deviations and then the squared deviations. But here we're still working on this version. So now we're going to take every value of x and square it. So 2 times 2 is 4. 1 times 1 is 1. 0 times 0 is 0. 1 times 1 is 1. And 2 times 2 is 4. So we just squared all the absolute deviations that got rid of the negative numbers, so we actually have a positive value. When we add this all up, this is called the sum of squares. I don't have to add this up for you. You can add that up. It's 30. Do that in text. If you added it all up, you would see 4 plus 4 plus 4 is 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 26, 40, 30, right? So we have the sum of squares. Now we have to get from the sum of squares to the standard deviation, and you might need a calculator. I put in our class materials that you buy this calculator. I'm going to teach this calculator. You're free to choose any other calculator you want, but I won't be able to give you any high-level direction on how that calculator performs because each calculator works a little bit differently. But if you choose this calculator, it's about $9 or $10 from Amazon. I have included that in my announcements, I believe, and also in the syllabus. You can watch the calculations that I enter, and you'll be able to sort of follow along. All right, so let's first look at the next step. The next step is to calculate, now that we have the sum of squares, we want to calculate the variance. The symbol for variance, if it's a population, is sigma squared. If it's a sample, it's s squared. And the formula is sum of squares divided by n. If it's a population. If it's a sample, it's sum of squares, as I said before, but it's n minus 1. Notice that I'm using lowercase n because it's a sample. All right, so let's figure this out. So the sum of squares we discovered is 30. 30 minus 20, because that is n. But over here, if it's a sample, we would still use 30, but n minus 1 is 19, right? So if we calculate that, 30 divided by 20 equals 1.5. If it's a sample, 30 divided by 19, we get 1.578. And it's a good idea just to round up to 2 decimal points. And because we have 0.578, we're going to round that up to 1.58. We'll talk a little bit more in coming weeks about what is the difference between the variance if it's a sample population versus the variance if it's a sample. You'll notice that the variance for the sample is slightly bigger than the population, and there's a very specific reason why. You'll also notice that when the denominator of something that you're dividing, when the denominator is smaller, the quotient, the result, is slightly bigger. For instance, let me do this very quick demonstration. 1 over 5 is 20. 1 over 4, which is smaller, is 25. 1 over 3 is 33. 1 over 2 is 0.50. So every time the denominator got smaller, the product got bigger. That'll come in handy in future weeks. Just adding a little seed. So now we have the variance. Now we're looking for the standard deviation. The formula for, or the symbol for standard deviation for population is just sigma. And the symbol for standard deviation for sample is just S. And we're looking for the square root of the variance. The square root of the variance, right? So with this calculator, you'll see that there is a second key, and there are keys that are buttons that have writing on top of the button, and there's sort of writing in front of or on the calculator, the face of the calculator. So what I'm looking for is the square root. So to access that, I press second first, and then the square root. And you can see that the calculator is now ready for me to enter in the variance of the population, which we discovered was 1.5. So the standard deviation is 1.224. We can round that down to 1.22. And for the sample, we're looking for the square root, again, second, and square root button of 1.58 and 1.256, which we can round up to 1.26. Oh, that should have just been the answer. 1.26. And see, those are the steps to go from that off population, we did that sample, we did the sample deviation. We did all the steps, and we went from the data set, the sum of the data set, we got the mean or the average. We subtracted the average from each value of X for the absolute deviations. We added them up, made sure that they were 0. That way we could proceed. We squared every absolute deviation and added them all up. That gave us the sum of squares. Then we further reduced the data by looking at it if we were creating the variance of a population. Sum of squares divided by n, or 30 divided by 20, and it's 1.5 if it's a population. If it's a sample, sum of squares, again, which is 30, divided by 19. So 30 divided by 19, 1.58 is the variance for a sample. Then we went further to the standard deviation. It's really just the square root of the variance. So the square root of 1.5 is 1.22. The square root of 1.58 is 1.26. And that's how we would create or reduce the data using the absolute and square deviations. Let's take a look at the other way of getting the sum of squares, because you can get the sum of squares quite easily without doing the absolute deviations, but there's a little bit more work that you have to do to understand the formulas. It's not that difficult. Let's do it. So here, all we have to do is square. I didn't have the instructions here. We can just cross that out for now. I'll just walk through it. 9 squared, 8 squared, 7 squared, 6 squared, 5 squared. Right, just the number times itself. 9 squared is 81. 9 times 9 is 81. Add 3 of those. 8 squared, or 8 times 8 is 64. 7 squared, 49. 6 squared, 36. And 5 squared is 25. All right, so when we sum all the squared x's and you add all of those, you can see that in the chapter on page 64. I don't have to do that calculation for you. You could do that. It is 1,010. All right. So the other thing we need, if we're going to calculate or reduce the data using this method, the way that I showed you first is called the definitional method of calculating data. This is definitional formula. This one's called the computational formula, and you'll see why in a second. We need, again, the sum of x, which is 140, but we also now need the sum of x squared. In other words, 140 times 140. All right, we could do that very easily. This time we're going to use the square button. I'm going to activate that without pressing second. So just 140 squared, hit equal, 19,600. Okay, so we have the sum of all the squared x's, and we have the sum of x squared. Now the formula for creating the sum of squares without doing all the absolute and squared deviations is this. We take the sum of all the squared x's minus the sum of x squared divided by n, or in this case, n, no matter which it is, right? The difference between this sum of x and this sum of x is the parentheses. Here we're taking the sum of all the squared x's. Here we're taking the sum of x first, which is 140, and then we're squaring it. And then we're dividing that by n. So let's put the values in. The sum of all the squared x's is 1010 minus the sum of x squared, which is 19,600 divided by n, which we said n was 20, or n was 20, right? So let's reduce that. 1,010, let's see what 19,600 divided by 20, which is 980. 1,010 minus 980, you'll be surprised, it's 30, right? Look what we got over here. We got the same value for sum of squares 30 here as we got here, but we didn't have to do the absolute and the square deviations. We just simply squared the x, every x, got the sum of all the squared x's, and used this formula to calculate. From that point, we use all the same formulas that we use. So we could say we're doing the variance or sample, sum of squares divided by n. We're doing it for, sorry, this is for population. For sample, it's sum of squares divided by n minus 1. I'm not going to do that again because it's all the same values. Then we need the standard deviation, which is the square root of the variance, the square root of the variance. We got that as still the same thing. 1.22, 1.25. Sorry, that's the wrong one. That has 1.5, 1.58, 1.22, and 1.26. These are, you just saw the one that I used for my notes before I practiced to make sure it all fit on the page. So, having said that, hopefully that is instructive, helps you see the calculations, helps you understand how what's happening, whether you're using the definitional formula or the computational formula. I'm going to post, as I said, another data set for you to practice so that you have some practice and opportunity to earn some extra points. All right, I'm looking forward to seeing your work this week. I'm looking forward to seeing how you deal with these very important concepts, measures of central tendency and measures of spread. Have a great week, and I'm looking forward to seeing all the calculations and all the statistics you probably